Welcome to this explainer. If you've ever looked at a beautifully complex engineering simulation, maybe a car crash test or an aerodynamic wind tunnel model, you're actually looking at the end result of some absolutely incredible hidden math. Because before a single physics equation is ever calculated, we somehow have to turn messy real-world reality into perfectly ordered mathematical grids. So today, we're exploring the invisible algorithms that power finite element preprocessors. These are really the unsung heroes that make modern engineering simulation even possible.
Think about this for a second. How do you actually translate reality into math without completely frying a computer? When you import a CAD model of, say, a jet engine, you aren't just bringing in a picture, right? You're importing millions of discrete geometric entities. Processing, stitching, and meshing all of those surfaces takes a mind-boggling amount of computing power. If the software just brute forced its way through, literally comparing every single entity against every other entity, well, your workstation would be frozen until the heat death of the universe. So the secret here lies in highly optimized, mathematically brilliant algorithms.
Okay, let's dive into this. We're going to follow a piece of geometry down a sort of digital assembly line, tracking it from raw import all the way to a solver-ready matrix. We'll hit 5 key steps. First, taming the raw geometry. Second, discretizing 2D surface areas. Third, filling the 3D volume. Fourth, validating mathematical mesh quality. And finally, number 5, preparing pre-solver kinematics. Starting with stage 1, taming the raw geometry through spatial searching and stitching.
So, when CAD models are first imported, they are notoriously messy. There are disconnected surfaces literally everywhere. To stitch them together, the algorithm has to figure out which edges match up. But comparing every single edge against every other edge gives us an O of n squared complexity. In algorithmic terms, that equals computationally infinite time. It's a non-starter. The elegant solution here is spatial partitioning, using things like KD trees. By dividing the 3D space into a hierarchy of bounding boxes, the software only searches within a specific zip code. That clever trick drops the search time down to a lightning-fast O of n log n.
Once we've isolated those edges in the exact same bounding box, the algorithm applies a simple Euclidean distance formula. It calculates the discrete points between the edges, and if that distance is less than your set cleanup tolerance, boom, the algorithm forcefully snaps and collapses those messy, disconnected lines into a single, shared topology line. This simple bit of math saves you from having to manually click and merge thousands of individual edges. And just like that, the geometry is finally stitched.
Moving down the line to stage 2, discretizing 2D surface areas. This is where we have to balance absolute computational speed against some very strict geometric rules. To fill a 2D surface with quadrilateral elements, the preprocessor relies on what are called paving algorithms. Imagine this process animating in your head. First, the algorithm identifies the outer boundaries of the surface. We call this the active front. Then it projects inward, generating these complete concentric layers of quad elements hugging that boundary. It continuously shrinks those layers inward, almost like ripples in a pond, but running in reverse. Finally, when those shrinking rings inevitably crash into each other in the center, the algorithm uses complex intersection logic to handle the overlaps and perfectly close the mesh.
But, as you can probably guess, those initial meshes are usually pretty jagged, which would create artificial stress concentrations. Enter Laplacian smoothing. It's a simple but incredibly powerful algorithm. It takes that jagged mesh and iteratively repositions the internal nodes. By calculating the exact centroid of all the neighboring nodes, it slides the target node perfectly into place. The result? A beautifully smooth, highly uniform 2D mesh.
All right, let's scale up to our third stage, filling the 3D volume. Going from flat 2D shells to 3D solid volumes introduces an absolutely exponential leap in mathematical complexity.
For 3D tetrahedral meshing, the absolute gold standard algorithm is Delaunay triangulation. To build these 3D pyramids, tetrahedra, the algorithm inserts nodes into the volume based on a remarkably strict geometric law called the empty circumsphere rule. This rule mathematically guarantees that if you were to draw a 3D sphere around the 4 corners of any generated tetrahedron, no other node in the entire model will fall inside that sphere. By enforcing this, the algorithm maximizes the interior angles and physically prevents the software from creating collapsed, useless sliver elements that would just completely ruin our physics calculations.
But what if you need 3D hexahedra brick elements instead of pyramids?
Well, here's a kind of fascinating industry secret. A fully automated universal hex meshing algorithm for any arbitrary shape doesn't actually exist yet. No way, right? Because of that, the software has to rely on sweeping and extrusion. It takes that flawless 2D quad mesh we generated earlier, applies vector calculus, and mathematically projects it along a trajectory. It basically generates those 3D brick elements layer by layer until the entire volume is full.
Which brings us to stage 4, validating mathematical mesh quality. This is absolutely crucial for preventing fatal solver errors down the line.
Here's the thing. If we don't validate the mathematical perfection of the shapes we just generated, our physics solver is just going to completely crash. So how does a computer actually know if a shape is good or bad? It uses isoperimetric mapping. The algorithm takes your physical element, which has real-world, slightly distorted x, y, and z coordinates, and it translates it back into a normalized, perfect parametric space. Think of it kind of like taking a crumpled piece of paper and mapping it mathematically to a perfectly flat, perfectly square grid so it can calculate the Jacobian matrix.
Now, the key number to know here is 1.0. The determinant of that Jacobian matrix tells us exactly how much the element's volume changes during mapping. A mathematically flawless, perfect element has a Jacobian determinant of exactly 1.0. If the element is badly distorted, that number drops. And if it drops to 0, or even worse, goes negative, that means your 3D element has fatally turned inside out. If you try to send a geometry that exists in an inverted spatial dimension to your solver, well, it won't just fail, it'll throw an error that makes you question all of your career choices.
We also have to check for warping. For a 2D quad element, all 4 of its corner nodes should theoretically lie perfectly flat on a single plane, but reality often forces them to twist. The warp angle algorithm handles this by splitting the quad into 2 triangles. It calculates their surface normal vectors using a cross product and then measures the angle between them. If the element bends past your set degree threshold, it gets flagged bright red right away for you to fix.
Finally, we reach the end of our digital assembly line. Stage 5, preparing pre-solver kinematics, which is all about contact setup and penetration checking.
Okay, so our parts are beautifully meshed and mathematically validated. But now, we have to tell the software how they're actually going to interact in the physical world. This is where bounding volume hierarchies, or BVH algorithms, come into play one last time. When we're setting up 2 pieces of metal crashing into each other, we define master and slave contact surfaces. The BVH algorithm runs a highly efficient check to see if the assigned physical thickness of a slave node is magically clipping through a master segment. Just like a glitched video game where a character's arm phases straight through a solid wall, BVH algorithms act as the final quality gate. They ensure that mesh overlap literally never happens in our engineering simulation, giving you the chance to subtly translate the mesh and resolve any penetrations before you hit solve.
And just like that, the entire process is complete. These algorithmic families have worked together in perfect harmony to turn raw, messy CAD shapes into a flawless, solver-ready mathematical matrix. Honestly, the amount of invisible calculus happening every single time you simply click mesh is staggering. So I'll leave you with this provocative thought. The next time you drive over a bridge or fly in an airplane, ask yourself, how much of your physical safety is directly reliant on the mathematical perfection of a Jacobian determinant? Keep learning, keep questioning, and I'll catch you in the next explainer.